Welcome to Lecture 4.5, the Spectral theorem. We will continue our assumption throughout this lecture that K is algebraically closed and that X is an n-dimensional vector space over K. Recall that a generalized eigenvector of a linear map A is any vector with the property that A minus lambda I to the m times V is 0 for some power m. The spectral theorem says that for any linear map A, our underlying vector space X has a basis of generalized eigenvectors of A. Let's recall our running example that I have shown in several previous lectures, which is a linear map with characteristic polynomial t minus lambda to the 11. So it has one eigenvalue with algebraic multiplicity 11. And it has 4 eigenvectors. In other words, the dimension of the null space of A minus lambda I is 4. In other words, there are 4 linearly independent eigenvectors of A that get mapped to 0 by A minus lambda I. Now what we usually want is a basis of eigenvectors of our entire space. But if we have a linear map like this, and we only have 4 eigenvectors, we obviously can't get that. So the idea of the spectral theorem is that we can at least find vectors that map onto these eigenvectors. In other words, maybe there are vectors v2, w2, and x2 that map onto v1, w1, and x1. These are generalized eigenvectors because A minus lambda I squared sends these things to 0. Now, here we have 7. If you believe that these eigenvectors are going to be linearly independent, these generalized eigenvectors, then this is a 7-dimensional subspace. And we still have an 11-dimensional space. So we don't have a basis. So there might be vectors v3 and w3 that get mapped on to these. These are also generalized eigenvectors because they are in the null space of A minus lambda I cubed. And we can keep going. Now we have 9 linearly independent vectors. Again, still unproven. We will prove that later that these are linearly independent. So we can pull this back and get a v4 and a v5, and now we have 11 linearly independent vectors and hence a basis of our underlying space X. If we let nj denote the null space of A minus lambda I to the j, then it's easy to see that if I is at least as big as j, then the null space of I is going to contain the null space of j. So we always have this increasing sequence of subspaces. Up here, n1 is the span of the eigenvector, so this is n1. n2 is the span of these 7 vectors. So this is 4-dimensional, this is 7-dimensional, n3 is going to be 9-dimensional, n4 10, and n5 11-dimensional. And then it stabilizes. n6 is equal to n5, and so forth. So notice that, for example, n3 is the set of all vectors such that if you apply A minus lambda I 3 times, it gets sent to 0. So what we will do in this lecture is we will define the eigenspace of lambda, so E lambda, to be basically all of these things. So one way to write that is it's the union from j equals 1 to infinity of nj. So obviously this is, in this case, equal to j equals 1 up to 5 of nj, because we don't ever get anything by going beyond 5. So the spectral theorem, where we are going with this, is we can always write X as a direct sum of eigenspaces in this manner, or I call them generalized eigenspaces. So lambda, or E lambda 1 up to E lambda k, where these are the distinct eigenvalues. Now we won't be able to prove everything about this picture in this lecture. What we will prove is that for each lambda, there is a basis of eigenvectors like this. what we won't be able to prove just yet is that these eigenvectors come in these so-called chains. For example, it's going to be clear why there has to be an v5 here. Why can there not be a v4 prime that also gets mapped to v3? And in fact, there will be other vectors that get mapped to v3, but these will be equivalent in some quotient space. So again, we will show that for any lambda, there is going to be a basis of generalized eigenvectors of, we'll call that E lambda, and the dimension of this is going to be equal to the algebraic multiplicity of lambda, which is the degree of t minus lambda, which is the degree of t minus lambda in the characteristic polynomial. And then in the following lecture, we will actually construct this basis and show that they have to come in chains like this. Okay, so that is an overview as to where we are going in this lecture. Let's get going now to prove the spectral theorem. Our first task at hand involves polynomials over a field, and it basically just follows from the division algorithm and the fact that K of t is a Euclidean domain. So let's let P and Q be polynomials over K that are coprime. Since K is a field, this is equivalent to saying that P and Q have no common roots. Then I claim that we can write AP plus BQ to get 1 for some polynomials A and B. And let's compare this to the integers, where a basic fact from number theory, or likely just your intro to proofs class, says that if the GCD of, say, x and y is some, let's call it d, then we can write ax plus by equals d. And in fact, d is the smallest positive integer that we can do this for some integers a and b. And this holds because the integers is a Euclidean domain, which means basically the Euclidean algorithm or the division algorithm work. And so is this ring. Now recall what the division algorithm tells us over Z. It means that we can write, so given, let me say it this way, given m and, or actually, how about if I say given n and d, where d is non-zero, we can write, or we can divide d into n and get n equals qd plus r, and r is the remainder, which is between 0 and d. So it could be 0, but it's strictly less than d. So for polynomials, we can do the same thing, but now our norm, instead of being just the absolute value, is going to be the degree. So in other words, over kt, we can write n of t equals, so if we have polynomials n and d, so we can divide d into n, d of times q of t plus r of t, where I should say that the degree of r is less than the degree of d. So there's a little bit of background that I know I repeated from my previous lecture, but let's go with it. So let's actually do the proof of this now. This should remind you of what we did, I think, in the previous lecture, where I'm going to let I be the set of all things that I can write of this form, AP plus BQ. So AP plus BQ, where A and B are polynomials over K. Okay, now, all I need to show is that this contains 1. Or actually, this contains any non-zero constant, because we're over a field, so if I have something that's non-zero, I can just scale to get 1. Okay, so this is technically the ideal generated by P and Q. And if you don't know or remember what an ideal is in ring theory, that's fine. Just know that it's all linear combinations. So it's closed under addition, subtraction, and multiplication by any polynomial. So what we'll do now is let's let D be the non-zero element in I of minimal degree, or D is any, because up to scalars, right? So D is an element of I of minimal degree. And we're going to, well, I claim that D divides P and D divides Q. And because there are no common roots, if P equals some, so let's write out the roots of P. I don't know if I need to really do this, but why not? Say lambda 1 up to lambda n, and say that Q of T is D times T minus mu1 up to T minus mu m, and these are all distinct. If we have a polynomial that divides both of these, that polynomial has to be constant. So this is all that we have to, this is all that we need to show. And then we're done. And now there's nothing special about P and Q. They're both, by symmetry. I just need to show that D divides one of them. And then by the same argument, it will divide the other. So let's take P and let's show that D divides P. So we will use the division algorithm and we will write P equals some quotient. Now I've used Q, so I need to use some other letter. Let me use G times P plus R. G looks like a Q, but the tail just goes the other way. And the degree of R is less than the degree of D. Oh, sorry, this has to be a D, not a P. So GD plus R. And now I will solve for R. This is what I did in the previous lecture. So we can write R equals P minus GD. So now we have a polynomial that has degree strictly less than D, and D had minimal degree for non-zero polynomials. Now that's not a contradiction. That tells us that R has to be 0. So that tells us that R equals 0. And now we come back here, and if R is 0, that means that P equals GD. Or in other words, that same thing as saying D divides P. And that is all that we needed to show. For our next lemma, let's continue with polynomials P and Q that are coprime and a linear map A from X to itself. For our next lemma, let's take a linear map A and coprime polynomials P and Q, just like up here. There are 3 natural null spaces to look at. We can look at the null space of PA, of Q of A, and P of A times Q of A, which we will denote by NP, NQ, and NPQ, respectively. Then what this is saying is that the null space of P of A, Q of A is the direct sum of NP and NQ. Before we prove this, let's get a little bit more intuition. So X is in the null space of P. What does that mean? That means that P of A times X equals 0. X is in the null space of Q if and only if Q of A times X equals 0. And X is in the null space of PQ if and only if P of A, Q of A, X equals 0. Now because these are polynomials in A, they commute. So that's the same thing as saying Q of A times P of A times X equals 0. So notice, if X is killed by P of A, then clearly X is going to be killed by q of a, p of a, because that is going to be 0. Similarly, if x is killed by q of a, then it's clearly killed by, it's in npq as well, because q of a, x is equal to 0, so this whole polynomial times x will be 0. So in other words, this tells us, this shows right away that np is contained in npq, and also nq is contained in that as well. So what I claim is that this is, everything in here can be represented uniquely. In other words, every vector that's killed by p of a times q of a is killed by either p of a or q of a. So there's nothing else in between. So that's one thing that I claim. So let me write that down. My first claim is that everything in PQ can be represented as NP, as something killed by P and something killed, or everything in NPQ can be represented as a sum of something in NP plus something in NQ. In other words, yeah, I argued that over here. Let's keep going. So this just says that NPQ is the sum of these two subspaces. And remember what it means for this to be the direct sum. Well, that means that, first of all, it has to be the sum, but also these are complementary subspaces. So they intersect trivially in the 0 vector. Now, another equivalent way to say that this is a direct sum is that everything in here can be written as a sum of something in here and something in here uniquely. So let me say that. So everything in NP can be represented as something, I'll say, as a sum of xp plus xq, where xp is in NP, xq is in NQ. Well, this we get from the previous part, but what's new here is this uniquely part. So this decomposition is unique. So we will show these one by one. So first, let's show that NPQ is the sum of these two vector spaces. And to do that, what we will do is use this lemma, and we will write 1 as AP plus BQ, and then we will analyze that. So let's do that first. So let's write A of t, B of t plus B of t, Q of t equaling 1 for some A and B. We know we can do that. And now what we will do is we will plug in A. And the right-hand side, we will get the identity matrix. And the left-hand side, we're going to get something that we claim is not going to be the identity. So let's do that and see what happens. So let's plug in A. And we get A of big A, P of big A, plus B of big A, Q times big A equals the identity. And now we will take this and we will multiply this by, on the right, by a vector in NPQ. So let's multiply by some x in NPQ. And if we do this, we get A of A, P of A, x, let me do this in red so you can see it, x plus B of A, Q of A, x equals I times x, which equals x. So I have just taken an arbitrary element in NPQ, and I claim that what I have done is I have written it as a sum of something in NP and something in NQ. And to see why that is, let's look at this P of A times x and this Q of A times x. So because x is in NPQ, that means that by definition, P of A Q of A x equals 0, or equivalently, Q of A P of A x equals 0. So notice that this entire first term, if I multiply it on the left by Q of A, so let's think about what happens if you multiply this by Q of A. Now these polynomials commute because they're polynomials in A. So if I multiply by Q of A, we get P of A Q of A times x, and that's 0. So in other words, this entire term here is in NQ. It's killed by Q of A. Similarly, this entire term here is killed by P of A. If I multiply on the left by P of A, I get P of A times Q of A times x. So this is in NP. I have just taken an arbitrary element and written it as something in NP and something in NQ. So that confirms part 1. Now for part 2. How do we show uniqueness? Well, let's suppose that there's 2 ways to write x. Let's write that as let's say that x equals xp plus xq, and also x prime p plus x prime q, where I'm just going to say it, I'm not going to write it. xp and xp prime are in NP, and xq and xq prime are in NQ. So we'll take this and we'll move both the xp's to the left, same side, and the xq's to the other side. So in other words, we get xp minus x prime p equals xq prime, or x prime q, however you want to say it, minus xq. Now this, because these are subspaces, this is in NP and in NQ. So this is in NP and NQ. Now remember, to show that this is a direct sum, we have to show that this is precisely the 0 vector, that they intersect trivially. Okay, so how do we do that? Well, first of all, let's give this thing a name. Let's call this z, because we want to show it as 0. And what I will do is I will show that this is 0 by taking z and multiplying it by the identity matrix, which we know is this expression right here, a of a, p of a, plus b of a, q of a. If I can show that z is killed by this expression, which is the identity matrix, then z has to be 0. Okay, so how do I want to write that down? So multiply by I. So let me box it. So I'm going to multiply this by this I. So a of a, p of a times, well, let's do first b of a, q of a, this entire thing, times z, equals I z equals z. So what happens here? Let's break this into two parts. A of a, p of a times z plus b of a, q of a times z. Now remember, z is killed, or z is in both of these. So z is killed by p of a and by q of a. So that must be 0, and that must be 0. So therefore, this is equal to 0. So I've just showed you that an arbitrary element, or let's see, what have I showed you? I've showed you that this decomposition is unique because the difference, z, has to be 0. And that's how we establish uniqueness and how we establish that this is a direct sum. It is straightforward to extend lemma 4.9 from 2 polynomials to k polynomials. I won't even bother reading this thing. I think it's easy enough to look at and see that it's true. And let's talk about why we care to do this. So let's let P of t be the characteristic polynomial of A. So we can write P of t as t minus lambda 1 to the, let's say, m1 times t minus lambda 2 to the m2 all the way up to t minus lambda k to the mk, where these are distinct eigenvalues. Now let's call this P1, let's call this P2, and let's call this pk. And think about what happens when we plug in A. By the Cayley-Hamilton theorem, P of A is the zero map. So the null space of P of A, the null space of the zero map, is everything. So in this case, this space n sub P1 up to Pk is equal to X. So that means that everything in X can be represented uniquely as a sum of things in these individual npj's. And think about what that is. So np1 is the null space of A minus lambda 1 I to the m1, and so forth. And pk is the null space of A minus lambda k times I to the mk. These are spaces of generalized eigenvectors. This is precisely the set of all generalized eigenvectors for lambda 1, and so forth. So everything in X can be represented uniquely as a sum of generalized eigenvectors for each eigenvalue. There it is. I've basically proven the spectral theorem. I will finish this lecture with a slightly stronger, reworded version of the spectral theorem that speaks in terms of generalized eigenspaces instead of generalized eigenvectors. So let me remind you of the definition of a generalized eigenspace. I think I wrote it in the margin on the first slide. So if A is a linear map from X to itself, and lambda is an eigenvalue with index d lambda, then the generalized eigenspace is just the null space of A minus lambda I to the d lambda, which, as I said before, is the sum of all A minus lambda I to the j up to from 1 to infinity, that we can really stop at d lambda. Now this is still the better definition because for infinite dimensional spaces, and I will show you one in a couple lectures involving differential operators, sometimes this sequence gets bigger and bigger for all j. So in other words, this sequence doesn't stabilize like we saw in our 11-dimensional example. Our strong version of the spectral theorem, which is pretty easily seen to be equivalent, is that if we have a linear map with distinct eigenvalues lambda 1 up to lambda k, then X is a direct sum of eigenspaces e lambda 1 up to e lambda k. So let's prove this. And we will let P of t be the characteristic polynomial and write P of t. So it's really not much different than what I just did. So I'll do it kind of quickly. T minus lambda 1 to the m1 all the way up to t minus lambda k to the mk, which we'll call P1 up to pk. Then the null space of P of A, which I've already explained is X because that's the null space of the zero map, is the null space of P1 of A, the direct sum of this, up to the null space of pk of A. So this, of course, is the null space of A minus lambda 1 I to the m1 plus the null space of A minus lambda k I to the mk. So this says that everything in X can be represented uniquely as a sum of generalized eigenvectors for each eigenvalue. In other words, for any x in X, X equals x1 plus x2 plus all the way up to xk, where xj is in the null space of A minus lambda j I to the mj. So these are generalized eigenvectors. Now I should actually finish with one comment. My original statement of the spectral theorem said there's actually a basis of generalized eigenvectors. And let me write out what that basis is. So if we let B1 be a basis of this, so how about if I write it down like this? Let Bj be any basis of the null space of A minus lambda j I to the mj. Then I claim that, well, I don't need to claim it. We know that a basis for the direct sum is just a union of the bases of the individual factors. So B is equal to, so a basis for X is just a union of these individual bases. And each one of these consists of generalized eigenvectors, because each individual space here is a space of generalized eigenvectors. Now X is not going to be a generalized eigenvector. It's a linear combination of them, but each one of these contains only generalized eigenvectors. And so therefore each basis is only going to contain generalized eigenvectors. So that's actually why my original statement of the spectral theorem is true. Okay, so to summarize, we have now confirmed that X will always have a basis of generalized eigenvectors of A, but what we have not yet been able to do is claim why the matrix with respect to this basis is going to be the Jordan canonical form. Well, I can't say with respect to any basis, but why we can always find a basis of generalized eigenvectors that looks like chains, as I've showed you before. So in other words, what I want to show you is that we can always avoid a case where we have branching like this. So if we do that, then for each lambda we have chains of generalized eigenvectors, and each one of these chains represents an invariant subspace. So in block diagonal form, those are going to be the so-called Jordan blocks. So that will be coming up in the next 2 lectures. I hope you stick around.